grade 12 University Prep Energy and Momentum Unit, looking at two dimensions. And this is the idea that sometimes things don't just hit head on. Sometimes they come at an angle, and certainly in your Crokinole lab, they will be on angles, okay? So the idea is that momentum is conserved, but it actually is conserved in both directions. So if something happens on a north and east angle sort of thing, the the momentum is conserved in the east-west plane as well as the north-south plane. Okay, and that matters. So the two equations then that you end up with is, really we don't care about the P equation because we don't use that. We use masses and velocities, right? So this is the equation, the first one that I'm sort of running my pen over right here, and then down here, which is the exact same equation. It's just that everything in the y direction and everything in the x direction. So what does it mean? It means when you have a question like this, you'd find everything in the x, you find everything in the y, and you end up resolving it using Pythagorean theorem and inverse of tan, like we've done a million times. Only know 5 things, I just know them very well, says Mr. Marco. This is the thing. I don't know, but every year, lots of kids, I'll give a question on angles, and then they forget to use 2 dimensions, and they get all confused. If you see a question that has angles in it, and it's somehow, it's a momentum or a collision or something, you have to do everything twice, in the x direction and the y direction. Okay? Similar to accelerations or anything else we do. You can't just add everything up. It just doesn't work that way. Okay? You have to do everything twice. So let's just see an example. Oh, we're not there yet, sorry. Yeah, that's all. So we're looking at x and y, so I've told you that already, okay? So here's the example. The typical one is a pool ball. I don't know why, I probably just took this from a book, but why a steel ball seems kind of lame. But anyway, a steel ball of mass that, moving with a velocity of 2 meters per second east, strikes a ball of mass this, initially at rest. Now, as you know, when you have a collision like that, if you hit it bang on, okay, that's great, it's one dimension. But if you hit it on an angle here, you hit it on the side, you're going to cause this thing to go that way and that one to go that way. This looks a lot like your Crokinole lab, okay? The collision is a glancing one, causing the moving ball to have a velocity of s afterwards, and the other ball to be 1 point. We don't know. We don't know the angle, or we don't know the speed of the little ball. Okay, so the big one, somehow you measure the final velocity with an angle. The second you don't. So just treat it right off as soon as you see an angle, right x direction, right y direction, and start dealing with it that way. So I go right ahead into calling x direction. I do conservation momentum in the x direction and then the y direction. So the stuff that I know as far as x direction data is for A, I'm just going to call, like it's actually, okay, we're doing north and east. So it's moving east, so it's all x, right? So the initial velocity of A is all x, 2 meters per second. The initial velocity of B in the x direction is 0. The final is 1.5. It's this component that would come down here, right? So it's 1.5 cos. It's adjacent to the angle, 30. B2x we don't know. And I know the 2 masses. So you just, you do this whole thing. It looks awful because all the subscripts, quite frankly, but, it's really no different. You solve for the B's velocity just in the x direction, right? And that's just using this conservation momentum formula, which you've done before, and isolate VB2x. Okay, so I'll let you write that out, but pause and write that out, and then I'm going to move ahead to the y direction. So as soon as you see an angle, just start solving things in the x direction, start solving things in the y direction, okay? Here we go. So in the y direction, they both initially have no velocity in the y direction. We know A2y has 1.5 sine 30. Sorry, I'm going to scroll here. I did call something positive. You do have to be careful because this is going to have a negative y component, right? VB2y, I don't have to write down, by the way, that it's negative. I'm looking for it. It'll turn out negative. If it doesn't turn out negative, then we screwed up, okay? And we know our masses. So exact same. We're just going to solve. Here's what we know. It's all 0 at the beginning, and the momentum in the y direction at the start is 0, right? So the momentum in the end has to be 0. That's all I'm really saying. So for VB2y has to end up negative, otherwise we screwed up. Okay, you know that you screwed up because it should be down. It doesn't make any sense for it to be up as well, because that would assume you had some initial up momentum. And like we always do, you get your x, you get your y, you draw a right angle triangle, solve for theta, solve for VB2, and there's your answer. Okay, and let's see if it makes sense. Again, I know I'm probably going faster than you, so you should be pausing, I realize that, but I'm going to jump up and see if this answer makes sense. 1.7. So after the collision, it's a little bit smaller. It's going 1.7, a little bit faster, and the angle was bigger or smaller? Bigger angle, which makes sense as well, because its y component has to equal this y component, right? So since this is, and this is of momentum, so since this is so much bigger, its y component has to be a bigger angle, right, to offset that, so they balance each other out. So anyways, that's the answer, that's the solution. I'm going to go with it as a good one, and I'm going to do another example on 2 dimensions in this video, and then I have like the granddaddy question of all the unit coming up. This and the dropping spring, vertical spring. Okay, so just check mark that and move on to the next example. Again, always pause when you need to. Okay, so here we go. This is a weirdly worded one. I took it straight from a textbook. 2 spacecrafts from different nations have linked in space and are coasting with their engines off, heading directly towards Mars. Okay. The spacecrafts are thrust apart by the use of large springs. So there's some spring that causes them to move apart. And what we're given is that this first one ends up on an angle of 5.1 degrees to its original. I always think that's an interesting language. So imagine I didn't give you the picture, you know, sort of being able to figure out that's what that means, right? So we're given kilometers per hour, 3,500 kilometers per hour. The next one's going 5.9% or degrees to the original, and we have its mass and its new speed. So it's asking us what's the original speed when it first started. Okay, so just because I use A's and B's, I decided to call A this one and B this one down here. So it is I call it a reverse inelastic because, you know, they were stuck together in the beginning and ended up separated, but really it's the same formula. And of course we treat it in 2 dimensions. So again, as soon as you see an angle, write down what you know in the x direction, write down what you know in the y direction. Okay. Here's something you might say, but Ms. Stone, you said to always use meters per second, and this is kilometers per hour. And so, yes, that's true. However, when you're dealing with the momentum formulas, if you're using all the same, like if everything's kilometers per hour, then you can stick with it. The reason is that if I wanted to put it in meters per second, I would just have to divide both sides by 3.6. So, you know, sort of doing the same thing to both sides of the equation doesn't change the equation, right? So it's okay. As long as I know that my answer, when you're using these conservation momentum, if you're given kilometers per hour, as long as everything's in kilometers per hour, it's okay. Okay, so I'm going to leave it. So this is what it looks like. Here's my positive direction. So in the x direction, everything stays positive. Okay. So sub in the numbers, and there's my initial velocity of the combined spaceship that were stuck together in the x direction. Oh, yeah, look at that. There was no initial y component, right? Almost by definition of the question. Now, if you didn't believe me or you weren't sure about that, you could, of course, go ahead and solve it in the y direction. But just by virtue of this question, it's saying that, you know, it's initially going this direction and everything is related to that original x direction. If you didn't believe me, you could solve it in the y and you'd get 0. Okay, you could solve it and get 0. So anyways, there's my answer. 3672. So let's just look at the numbers and see if that makes sense. So it was going sort of right in the middle of the 2. And does that make sense? That this one ends up going faster and that one's up going slower. B is lighter, so it makes sense it's going faster and at more of an angle. So Yeah, I mean it's within the numbers given in the question for sure. So let's check mark it. Okay, so that's it for this one. I'm going to stop this video and we'll do the Grand Poobah in the next example.